All right, everybody, just get my focus lock. Okay, let's do a conservation of energy problem with rotational kinetic energy. Couple important things to point out to you here. All right, so let's see here. We've got, let's just look at like something sliding down a hill the way we used to do it. The way, something sliding without friction, right? Something slides down a hill. It goes from gravitational potential energy into kinetic energy at the bottom. And we've always just done mgh equals 1/2 mv squared. No friction or anything. The m's cancel. You get v equals radical 2gh. That's our gold standard here. This is our equation we want to have in our head when something slides down a hill or we drop something and there's no drag or friction or air resistance. The speed it achieves is radical 2g times however far it's fallen down vertically. All right, not the straight line distance, the vertical change in height. Right, that's what h is representing. So when we talk about something rolling down a hill, all right, so if we just look at let's do the hollow hoop. Hollow hoop rolls down a hill, right? Well, that's a little bit different. As this object is rolling without slipping, this is important, it's rolling, it's moving forward over the center of mass, so to speak. So it's a hollow hoop. The center of mass is moving with some velocity. We usually just call that v. Sometimes we call it vcm, but usually we just call it v. And it's rotating. So if we track a little piece of the ring, it's moving in a circle while also moving forward. It's moving forward. So this little part of the hoop is moving forward with all of the mass at the v, and it's also rotating around at omega. All right. Well, the rate at which all of this mass is moving forward is equal to the rate at which the outside of the hoop is passing along the ground, right? It's like if we find the tangential speed of this hoop, vt equals r omega, that's how fast this hoop's moving around in a circle. That's how fast the whole thing's getting propelled forward. All right? So when an object's rolling without slipping, it moves forward at the rate of that its outermost edge is rotating. It's kind of interesting. So v of center mass equals r omega. So when something rolls down a hill and it achieves some sort of velocity at the bottom, it's still going from ug into kinetic. However, the kinetic energy has two components now, right? It has the rotational component and the translational. I usually write the translational first. I don't know why I just wrote rotational first. The translational, that is the component of the overall motion of all of the mass. It's the center of mass motion. All right, so a portion of the energy is going for the overall translational motion, and a portion of it is going into the rotational motion. So, okay, rotational. So mgh equals 1/2 mv squared. Okay, rotational is always 1/2 I omega squared. I is whatever the moment of inertia of the hoop is, the hollow hoop. I is simply capital M R squared. All right. And then omega, which I erased, but you can go back and get that, the omega is always equal to V over R. Now, sometimes you're given omega, the rotation rate, sometimes you're given the center of mass speed. So we're going to take these two equations over here on the left and put them into this equation here, and then we'll see a lot of cancellation occur. But I'm running out of space. Let me save the velocity up here of something just sliding down the hill, radical 2gh. We're going to save that. We're going to save that for to compare against, because your rotational one can never be greater than that. the velocity at the bottom of the hill nothing can ever be faster than that, because otherwise it must be getting some energy from somewhere magically. All right, so I'm going to rewrite the equation up here. Mgh equals 1/2 mv squared plus 1/2 I omega squared. All right. I'm going to put in I and omega. Now, I used lowercase m's in here. I use a capital M for my moment of inertia. They're the same thing in this case. In this case, they are the same thing. This M, and this M are all the same. It's just the mass of the hoop. So that's no big deal. So for this equation, I would have 1/2. Now be careful here, because when the moment of inertia has coefficients, it's very easy to accidentally drop the 1/2 in front of the I, or get confused between the coefficient and the 1/2. Happens all the time. I've done it many times. It just happens. And omega squared is v squared over, and don't forget, it's also r squared. And this r is capital R. It's the radius of the hoop. It's the same for this guy. It's v over capital R. There's a problem in the packet where there's a loop-to-loop, and I'll talk about that quickly after this, but there's the radius of the hoop, the loop, and the radius of the ball. Those are two different things. So sometimes when you're solving in terms of variable, you do have to keep in mind that you might have multiple different things that you're calling radius. So just be careful there. That's typically why we make the radius of the rotating object a capital R. And then if it's like something in orbit, like a circular centripetal motion, we make the radius of that orbit lowercase r. It's just something we do. All right, so we can cancel out a bunch of stuff. R squared cancels here, R squared cancels here. And again, what we're trying to do is figure out the velocity of something rolling, the hollow hoop rolling down the hill at the bottom. These two are coupled together, all right? The translational kinetic energy and the rotational kinetic energy have to agree with each other. This thing can't be rolling faster, right, than the center of mass motion. That means it would be slipping, which does happen sometimes. That is something that does happen. When that happens, typically you're calculating the rotational kinetic energy and the translational kinetic energy separately to figure out the total energy input or something like that. But anyhow, we couple it together using the equation that binds omega equals v over r to eliminate unknowns. So r's are canceling here. M's are going to cancel on both sides of the equation because every term has an M. So now let me kind of rewrite. And this is the way I wrote up the solutions for you. V squared over 2. And for this one, it ends up being, let me keep track here, also v squared over 2, which is kind of nice. You get GH. 1/2 plus 1/2 is v squared. You get the speed of the hollow hoop at the bottom is radical GH. Now, for something rotating, this is as slow as it will be. Radical GH. A hollow hoop is the ultimate, all the mass is concentrated as far away from the center as possible. All right, all the mass is in this thin outer hoop. This is the hardest thing to turn, a big hollow hoop, right? Because all that mass is concentrated. If you had a solid disk of mass M and a hoop of mass M, the hoop would be harder to turn because that mass is concentrated farther out from the center. All right, it requires more torque to turn it. It's the same thing, you know, rotational motion, translational motion, same concepts. You know, something with a greater mass is harder to get moving because of F equals ma. It takes more force to accelerate something with more mass at a given acceleration. Same thing here. So if you concentrate that mass in the outside, any torque that's being applied, it's hard for it to turn. So this is the slowest something will move rolling down a hill without slipping. So any other rolling object, it's got to have a speed somewhere between radical GH and radical 2GH. So you get things like 5/4 GH, 4/3 GH, 3/4 GH, 1/2, or no, I'm sorry. 5/4, 4/3, you won't get 3/4, you won't get 1/2 GH. It's got to be something greater than 1 in front of the GH. So just a kind of interesting tip that can be used for multiple choice questions very often. Like if you don't want to do it and you're like, okay, which speed can it be? And you see something less than radical GH, and you see something greater than radical 2 GH, then you know that's a wrong answer. All right. And this goes for, you know, pretty much anything, because another one that's very common, I'm not going to do the whole thing right now, but I had started making a video of this one earlier, but my phone ran out of memory, but I'm kind of glad it did, because it's a little more complex, but I have seen it multiple times on the AP exam, which I'm not entirely certain what it's going to look like, but it's a cart with 4 wheels, and they say the mass of the cart is capital M. The mass of each wheel is M/4, right? So the total mass of the system is M plus the 4 wheels, so it's 4 times M/4, so the total mass of the system is capital 2M. So then you set up, your conservation of energy. You have 2m GH at the top equals 1/2 of 2m v squared plus 1/2. Well, actually, it's got to be 4 wheels, so it's 4 times 1/2 I omega squared. All right, so you have the center of mass motion of all of the mass, the wheels and the cart together. You have the 4 wheels rotating as well. So that's a common one, and I'll leave that for later. Hint. Some point we'll do that one. All right, so there you go. Conservation of energy. See what you can do with those problems. I just finished up writing up the PDF solutions. I'm just going to post the whole, all of the solutions for that worksheet. All right, see you guys later.